beautiful, fascinating, destructive, deadly.
The volcano on Montserrat has erupted again. It sent rivers of molten rock towards the airport and set houses on fire in the abandoned capital, Plymouth. More than 4,000 inhabitants have now left the tiny Caribbean island, and the governor says if the exodus continues, life on the island may no longer be viable. Our correspondent Malcolm Brabant reports from Montserrat.
The volcano is now exploding with ever-increasing frequency and violence. Millions of tons of molten rock spew out with every eruption and squeeze the population into a rapidly shrinking enclave in the north. This latest spurt of activity has cost more than 20 lives, wiped out 2/3 of Montserrat's accommodation, and created more than 1,000 new refugees who urgently need help.
That news report and these pictures from the Montserrat Volcano Observatory illustrate some of the terrible effects of a volcanic eruption. But there's a whole lot more to a volcano than initially meets the eye. The devastation caused by falling rocks and molten lava are obvious, but there's another equally lethal side to a volcanic eruption. This is a pyroclastic flow, a deadly river of searingly hot gas and ash that rushes silently down the side of the volcano. As fast as a Formula One racing car, it suffocates everything in its path. It was a flow like this that wiped out the Roman city of Pompeii when Mount Vesuvius erupted in 79 AD. It's easy to see the effect a volcano has on its surroundings, but an eruption can also have a global impact. Some volcanoes throw gas and dust high into the atmosphere. Here, it's not what comes down that's important, it's what stays up. It can change the Earth's climate, which ultimately affects us all. To understand how this is possible, it's important to know exactly what a volcano ejects.
Actually, what you see coming out of the vent of a volcano is primarily condensed water and mineral ash particles. These fall out of the atmosphere fairly quickly. The smoke that we see that spreads over the entire planet is actually composed of sulfuric acid droplets, extremely small droplets, too small to see with the naked eye, but that are formed in the upper atmosphere when the sulfurous gases emitted by the volcano are converted by chemical processes in the upper atmosphere into sulfuric acid, which then condenses into this fine mist.
June the 15th, 1991. Mount Pinatubo in the Philippines erupts, throwing a huge number of microscopic particles, called aerosols, high into the atmosphere.
The aerosols probably went as high as 25 or 27 kilometers, well into the Earth's stratosphere. The amounts of material are estimated at about perhaps 20 million tons of sulfur dioxide. Of course, there was a large amount of ash also injected and water vapor. And that led to a significant enhancement by a factor of 100 of the background aerosol layer in the stratosphere.
High above the Earth, satellites monitored the progress of Pinatubo's stratospheric aerosols as they spread around the world. Initially confined to a narrow belt in the tropics, by July the 11th, they'd spread deep into both northern and southern hemispheres. And by August the 15th, they'd effectively covered the entire globe. Looking at a cross-section of the atmosphere, The aerosols were found concentrated at a height of 20 to 25 kilometers above the equator. The effect of the aerosols was seen on the ground by measuring the amount of sunlight arriving at a solar energy power station in Southern California.
Unfortunately, the amount of solar energy available to us coming down from the sky has been somewhat lacking compared to earlier years, and that was because of a number of effects. For one thing, we are seeing, we believe, the impacts of Mount Pinatubo's eruption quite a while ago. The upper level particles and sulfur dioxide that it put into the atmosphere are causing about a 5 to 10% decrease in the amount of radiation that reaches the surface. In addition to that, we've had somewhat of a break in a 6-year drought in this area. Normally we expect 30 cloudy days per year. That's what we model. We've seen quite a bit more than that this year.
The stratospheric aerosols from Pinatubo caused spectacular sunsets around the world during the remainder of 1991 and well into 1992. How much effect the aerosols have depends on how large the particles are and how long they stay in the atmosphere. Research aircraft have collected volcanic aerosol particles, such as these. The particles are incredibly small, only about 1/10,000th of a millimeter across. Their ability to scatter light did much more than produce dramatic skies. It reduced the amount of solar radiation reaching the Earth's surface.
Pinatubo put a tremendous amount of sulfate aerosols up into the stratosphere, which lasted for a couple years, and it cooled off the Earth, so the year 1992 was much cooler than 1991. The amount of cooling from Pinatubo was as large as the effect of all the greenhouse gases we put in the atmosphere up until then. So the net effect was cooling. It worked against the greenhouse effect.
Following the Pinatubo eruption, the evolving cloud of water vapor, sulfurous gases and aerosol moved westward and circled the Earth in approximately 22 days. But the effect on the temperature wasn't simply the straightforward cooling predicted. This map shows temperature anomalies in the winter of 1991 to 1992. Blue areas correspond to a temperature decrease by 1 to 2, sometimes 3 Celsius. Yellow to a small but unusual warming. And the red areas, temperatures as high as 4.3 Celsius above normal. The sulfate aerosols from the volcano went up into the stratosphere. In the tropics, it was heated, and this produced a larger than normal temperature difference between the equator and the poles. It made the jet stream stronger, producing a change in the pattern of atmospheric circulation so that more winds came from the south than usual, and that produced a much warmer winter in Europe and over North America.
So this dynamical effect, this effect on the atmospheric circulation, is sort of counterintuitive, because in addition to blocking out the sunlight and cooling a little bit, the change of the atmospheric circulation, the change of the wind direction, was a stronger effect, and it produced warming.
One effect that occurs when you have a sort of a slow emission of the lava rather than an explosive event is that the sulfurous gases tend to be emitted into the lower part of the atmosphere, and mainly into the troposphere, which is where we have weather, we have clouds, we have precipitation. And so the aerosols tend to have a considerably shorter lifetime or residence time in the atmosphere. It might typically be a week to several weeks. In an explosive volcanic eruption of a large enough size that injects the aerosols into the stratosphere, then the aerosols that form, the sulfuric acid aerosols, can have residence times of several years. And that makes considerable difference in the climatic impact, because it's not just the density of the aerosols that you have, but it's also the length of time that they're producing a net energy deficit at the surface.
In 1982, El Chichon erupted in Mexico. It produced vast quantities of volcanic ash which was tracked by weather satellites. But ultraviolet images revealed something else rising above the ash cloud. a plume of gas. Within 21 days, the plume had been carried in a thin band around the equator. The large amount of aerosol, 3.3 million tons of gaseous sulfur dioxide, lasted about 3 years in the stratosphere. But its climatic effect was nothing compared with the eruption of Tambora in 1815, which was at least 50 times larger. The year following Tambora was known as the year without a summer. Steve Carey explains why.
The Tambora eruption, which is the largest historic eruption we know of, caused a global cooling of about 1 degree centigrade. That may not sound like much, but actually when you look at some of the atmospheric disturbances on a regional level, it had very significant implications. The summer of 1816 here in New England was especially harsh, for example. There were a number of killing frosts which took place in June and August. These killing frosts caused widespread destruction of the agricultural crops here in New England. So on a local level, we can get temperature deviations that are tens of degrees, but over the globe, that averages out only to about 1 degree because other areas may in fact get warmer, whereas some other areas are cooler.
The data from Tambora and other eruptions show that there's a strong relationship between the gases ejected into the atmosphere and the associated climatic effects. This graph shows temperature decrease in relation to the amount of sulfur discharged from a number of eruptions. Mount St. Helens, Krakatoa, Katmai, Tambora. There's a good correlation between the amount of sulfur discharged and the global cooling associated with each eruption. This is a reconstruction of the opacity of the Earth's atmosphere, how difficult it is for light to get through. It shows the opacity of the 1815 eruption up to a period of 4 years. From the start of the eruption, there's a dramatic increase in the opacity of the atmosphere, so less sunlight reaches the Earth. It quickly reached its maximum, followed by a long period during which the atmosphere cleared up very gradually as the sulfuric acid dissipated through fallout. And this fallout, whether acid rain or volcanic ash, is preserved in ice cores, giving scientists vital information about ancient events. For volcanologists, a benchmark event was the eruption which formed the huge Toba caldera in Sumatra 75,000 years ago. The caldera is nearly 40 kilometers wide and 100 kilometers long. About 3,000 cubic kilometers of ash were erupted, which can be traced over much of the Bay of Bengal and even 2,000 kilometers away in northern India. There is also a sulfuric acid record in the Antarctic ice cap. The Toba eruption was so large, it's possible that it caused a fresh glacial advance during the last ice age. Explosive volcanic eruptions are spectacular, but they aren't the only way in which volcanoes influence the climate. There are other, much longer-lived outpourings. In 1783, 14 cubic kilometers of basaltic magma erupted from the Laki fissure in Iceland to form the largest lava flow in recorded history.
With such a large emission of magma, there is of course a tremendous emission of volcanic gas, and that includes fluorine, as well as of course a lot of carbon dioxide, water vapor, and sulfur dioxide. When fluorine is emitted from a volcano of this type, the fluorine is adsorbed onto ash particles and then falls to the ground and contaminates vegetation, and particularly contaminates grazing land. And of course this grass and fluorine is ingested by the grazing livestock, and this leads to fluorosis and a number of diseases that then affect the livestock, including gout, teeth falling out, and the inability of these animals to survive, and that leads to decimation of the livestock. And this actually brought about loss of about 75% of the livestock in Iceland because of this tremendous disaster. consequence of that, of course, was that the Icelandic population was greatly affected. Over a period of a couple of years after the eruption, there was a decrease in the population of Iceland by about 24%. The largest disaster that has occurred in Iceland in history was then thus brought about by this tremendous eruption, and it was the effect of primarily of the volcanic gases that brought about this human disaster. In this industrial world, the sulfur output from human activity is about 3 times the output from the Great Laki eruption. But of course, that is entirely into the troposphere. It is very short-lived in the atmosphere and therefore does not have global effects. The principal difference, of course, between a effusive or a lava eruption and an explosive eruption is that typically the effusive eruption is not associated with a very high eruption column, a few kilometers, as opposed to tens of kilometers in the case of an explosive eruption. If it was only within the troposphere, then the Laki aerosol would have had short-lived and minor effects because it would have been essentially rained out or incorporated into the normal circulation in the weather.
An even bigger event happened in an area of about 100,000 square kilometers between Washington State and Oregon in northwestern USA. It's known as a continental flood basalt. Each of the long, flat layers is a single basalt lava flow, erupted from a fissure similar to the Laki eruption in Iceland. About 5 flows are piled on top of each other here in the Columbia River Gorge. Most are 10 to 30 meters thick.
Flood basalt provinces are extremely important in earth sciences. They tell us about processes that occur when mantle plumes come up and impact the surface of the earth. A lot of the large dark patches you see on the moon are flood basalt provinces, so hopefully by working out the details of the emplacement of flood basalts on Earth, we can have applications to other planets as well. These so-called flood basalt provinces have punctuated Earth's history. One seems to come every few tens of millions of years. The theory is that a hotspot came up from the mantle and pierced its way through the lithosphere and erupted through the crust, forming this large pile of lavas about 17.5 to about 15.5 million years ago.
Total accumulation is roughly about 174,000 cubic kilometers, and in this general area here we're looking at probably close to 3 kilometers of basalt below us. As you go farther east, it thins to maybe 1 kilometer. There are at least 300 flows that we know of, and probably at least 50 beyond that we're starting to get a fair idea about right now. What we envision happening is that major pulses coming out in a fairly short period of time, maybe between months and years, and then perhaps long periods of time, as much as 20,000 years, between the next pulse of eruptions.
But the eruptions themselves, were they relatively quick events?
A newer theory, one that we're working on right now and testing out, is that they were in fact erupted very slowly, gradually covering great distances and very wide areas, much as the lava flows in Hawaii are doing at the moment, but on a much, much larger scale.
Watching a slow eruption is a bit like waiting for paint to dry. But gradually, these flows build up the massive stacks of lava we see in the flood basalts.
We see many stacks, or several stacks, within one eruptive unit. So the inference is that each one of those took probably months to a few years to form, and the whole pile many years to possibly decades.
Occasionally, the lava is brought to the surface in a much more spectacular way. Here, the lava is being erupted along a long, linear crack. But whether fast or slow, the result is a huge sheet of lava, often stretching many thousands of square kilometers. In the Columbia River province, these basalts were thought to have erupted onto a terrain which was like a gently sloping billiard table, going from the Idaho border down to the Pacific. But what was the environment like?
In the Pacific Northwest today, we find oak and conifers and a fairly temperate climate. But back 15 million years ago, when the Columbia River basalt lavas were being erupted, fossil tree remains from between the lava flows show that there were walnut, spruce, Douglas fir, ginkgo trees, large trees, bigger than today, showing that there was a luxuriant forest at the time, supported by a milder climate than we have at present. This is one of the Columbia River basalt's huge lava flows, about 2,500 kilometers. Where I've been looking at the flow, it's 80 meters thick, yet it's about 200 kilometers from its source. At the base of the lava flow, there were some tree molds, and in the wall of the tree molds you can see boxwork. This is a modern piece of carbonized wood, also showing the same boxwork, and the lava takes the impression of the boxwork and leaves it on the wall of the mold. This shows that there were really large trees, about 1.5 meters across this tree, growing in the path of the lava flow, and the lava gradually enveloped the tree and then carbonized it.
It is rare to find such splendid tree fossils. Often the best evidence of the dense forests, devastated by the lavas, is found in a carbon-rich layer, a bit like coal, right at their base. This layer was formed when the lava flowed over a mass of fallen trees.
I've reached in and pulled out this twig here. The twig is deformed by the weight of the lava above, and you can even see the tree rings that grew in this twig before it was destroyed by the lava flow and carbonized.
This is one of the great basalt lavas of the Columbia River province. It was erupted 14.7 million years ago. The lava here contains about 300 ppm, parts per million, of sulfur. From other measurements, it's known that when it was under the Earth's surface, the lava had about 2,000 ppm of sulfur.
So therefore we can show by simple calculations that 1,700 ppm of sulfur was erupted into the atmosphere as sulfur dioxide gas when this lava was vented. The volume of this flow is about 1,300 cubic kilometers, a staggering figure, very large, and therefore we can show that the mass of sulfur dioxide being put out into the atmosphere by the eruption was about 1.2 times 10 to the 13 kilograms. Enormous amount of sulfur. So a big eruption like this could really have a significant effect on the atmosphere.
In 1991, Pinatubo produced 20 million tons of sulfuric acid aerosol. By comparison, just one of these big lava outpourings in the Columbia River sequence released something like 50 times as much a year. If this reached the upper atmosphere, it would have a dramatic effect on the Earth's climate. Could it even endanger life itself?
I think if we can understand the climatic effect of the large flood basalts here in the Columbia River, then we can go on to future studies to look at the significantly bigger Deccan province in India, which of course was erupted at about the same time that the dinosaurs died out at the end of the Cretaceous period. And then we can address some of the major questions about mass extinctions and the role that flood basalt provinces have or might have had in causing mass extinctions.
Mass extinctions are controversial, especially the one at the end of the Cretaceous period 65 million years ago. Mike Rampino at the University of New York has spent much of his career researching them.
We're talking about 1,000 megatons of sulfuric acid aerosols produced in the atmosphere after a large flood basalt event. And that would be enough, if it gets into the stratosphere, of forming an optical depth in the atmosphere of possibly up to 10.
So again, equivalent to a Toba size?
Equivalent to a Toba size explosive eruption, yes. For Toba, 75,000 years ago, we could get up to a 90% drop in the direct solar transmission.
Which is what, like a moonlit night? Or?
Like a moonlit night, yes.
Now, many people have argued that the eruption of the Deccan basalts 65 million years ago were implicated in the death of the dinosaurs. What's the mechanism that would have caused that extinction?
If the flood basalts were involved in the extinction, the cut down of sunlight from the aerosols in the stratosphere at the time, cutting down on photosynthesis, cooling the climate, the effects of the rain out of the sulfuric acid, as acid rain on land and in the oceans, all of that would combine to possibly lead to pretty bad conditions on the Earth's surface, possibly contributing to the mass extinction.
There's always the real question here as to whether the volcanic aerosol from these large flood basalt events ever really enters into the stratosphere. Does it enter into the stratosphere and therefore bring about global change, or is it confined to the troposphere and therefore only of regional effect? I think that we don't really have a viable mechanism whereby volcanic activity from flood basalt eruptions can bring about global large-scale extinctions.
If you look at the dates of the mass extinction events and the best dates that we have of the flood basalt events, it turns out that there are at least 5 close coincidences, possibly up to 10 coincidences between times of mass extinction and the times of the flood basalt eruption. That leads one to think that either they're related in some way or they're both related to some other phenomenon which is triggering both the mass extinctions and the flood basalt events.
The idea that events like the mass extinction of the dinosaurs could be caused by volcanic activity is still open to debate. But one thing is certain: the uncontrollable power of a volcano can not only change the environment of those who live nearby, it can also have a huge impact on our global climate.
If you'd like more information about the Earth and Life series or the Open University, call us on 0541 596 955 or write to the Open University, PO Box 625, Milton Keynes, MK7 6AA. We also have a website and a CFAX page.